Before we begin, I want to comment that the homework 0 solution has already been posted on Blackboard, and there are multiple ways of answering the same question, so you can check for alternative solutions. And if you're having trouble with the homework 0, please check out the following links. If you need to review math in more details, you can see that even though the link is not showing full, you can still click them by downloading the PDF, and you can open the links by this way. And they talked about some basics on vectors and line integral, curl, gradient, and all the things related to fundamental vector analysis. I also want to comment on the homework 1, problem 1. So here you can see that this form is actually really similar to this divergence theorem. On the left hand side we have a volume integral, and on the right hand side we have a surface integral, except that del dot v is a scalar, and the scalar on the left and on the right instead here, and gradient of a scalar is a vector, so vector on the left and vector on the right. Now to relate the two, we can actually replace v by a constant vector times t, and if you apply the product rule, you will get back what you need to prove here on the left. I want to comment on the homework 1 problem 2D as well. So this problem, in principle, I'm asking the E field at any surface, at any space point, and however you might find that the integral is not particularly easy to do if it is off the z-axis. So if you can only give the result only on the z-axis, and I will give you full point already. And also in the question F, I asked what should be the force between these two hemispheres if I group them together, and then this problem can actually be viewed from a different perspective, in the sense that now since if we combine this together, we can treat this as the entire sphere that's with the charge density sigma that's equally distributed, and that actually can be viewed as sort of a conductor. And we already calculate the force on the surface of a conductor. If we can go back to lecture 3, we can see that the force actually should be proportional to sigma squared. And now if you apply this formula to half of the hemisphere, then say that's the hemisphere on top, and integrate over the entire surface, and that already gives you the force above hemisphere felt, and that is the force that you are interested in. So instead of going through complex calculation, you can find out the result in one simple integral. Also, in the question 5, you don't need to provide any derivation at all. You simply need to give a single number. I also received some questions on this hollow conductor on the last lecture. I think I have been a little bit quick and haven't been able to explain this in a clear way. So now let's look at this problem again. So here, to solve this problem, we can go step by step, and first we can look at the inner region. In the inner region, there is a point charge Q sitting here, and it can induce a surface charge on this edge of the conductor. And now if we do volume integral over that's enclosing this hollow regime. We know that the del dot E integration over this surface must be 0, and then this means the total charge inside should be 0, which means on the conductor the surface charge must integrate out to be minus Q, and this means that since the total charge on the conductor is 0, so the outer shell must have a charge of Q. And because this is a perfectly spherical sphere, then all the charge will try to distribute it evenly because they want to minimize the energy. So in the outermost shell, it can be described by a constant surface density. And if you calculate the problem of constant surface density and calculate the electric field, you can actually realize that this is 1 over r squared height direction because of the symmetry, and that is identical to a point charge in the center. Now let's start by looking at Laplace equation. The Laplace equation can be derived from Poisson's equation, and so assuming that there are no charge density here, rho equals 0, then we recover the Laplace equation. And many people actually say that electrostatic is the study of Laplace equation. Now let's look at 1D first. In Cartesian coordinates, the Laplace equation is here partial v squared and partial x squared, and this can actually be solved analytically because it's a simple PDE, and here v should be equal to mx plus b, where m and b are two constants that is unknown. If we specify the boundary condition, however, say that if we specify the boundary condition at 0 and 1, and then that can solve the m and b. Alternatively, we can specify the value at 0 on the slope at 0, and that will also give us m and b. To conclude, as long as we have two conditions, we can solve for m and b. And also, if we plot the plots the v as a function of x, we notice there's a straight line, and now we see that if we go equal distance to the left and to the right, the v in the middle is simply the average of the two. Mathematically speaking, it's vx plus a plus vx minus a divided by 2 equals to vx. This means that in the middle of this regime, there are no minima or maxima, and the minima or maxima can only happen at the boundaries. Let's look at the cylindrical coordinates. So in the cylindrical coordinates, let's say that the theta or phi direction is a constant and the v only depends on r. Then the Laplacian can be written as this one, and the solution could be either a constant, which is trivial, or could be a log of r, or they can be a linear superposition of the two. For the spherical coordinates, the Laplacian looks like this if we set v only depends on r, and there are again many solutions. One is a constant, and there is 1 over r. For example, you can study the problem homework 1 question 4, and there are a capacitor made of two shells of a sphere that share the same origin, and for this problem, because the VA and the VB are fixed values, it has a spherical symmetry, we can reduce the problem into 1D, and the solution immediately can be written down as alpha over R plus beta. And now we have two boundary conditions, VA and VB are known, then we can actually solve for alpha and beta. Now, these are the Laplace equation in 1D. This is still a PDE, so it's relatively simple. Now, in 2D, we actually have a differential with respect to x and y, and the solution might be much more complicated. For example, in Cartesian coordinate, a constant is a solution, and here in the polynomial of first order, there can be solution of x and y, or they can be a linear combination of any of these. We can also go to second order and find out one solution and the other solution. Similarly, on the third order, there are two independent solutions. And this list goes on, and there are infinitely many possible solutions. And likewise, we can calculate in the polar coordinates. The Laplacian looks like this one, and here we listed a solution that's originally from the 1D solution that only depends on R. However, we can add the solution that depends on phi as well. So you can see that there is a complicated phi dependency multiplied by a R dependency. You can check that the first term gives you m squared v, and the second term gives you minus m squared v, and these two cancel each other. Now, I claim that in the 2D, still there are no local minima or local maxima. How to prove that? Well, I can do a Taylor expansion and study the behavior around this local point of interest. Say that I can expand the x plus y, I can expand the v, the function of x and the y plus h in terms of near the point of x and y. And then this gives you vx and y plus h times partial y partial v partial y prime, where y prime is evaluated at y, and then there are higher order terms. But for simplicity, let's denote this complicated term of the y derivative evaluated at y as vy. Then we can write down the Taylor expansion for x, y plus h, x, y minus h, as well as x plus hy, x minus hy. Now we notice that these first order terms cancel each other, and the third order terms cancel each other. And what's left over are four terms on the left here, and 4vxy here, and also second order derivative terms here. So it combines to h squared vyy plus vhxx. However, we notice that this is simply the Laplacian evaluated at x and y, which gives us 0. So this means that in the end, the scalar potential at x and y can actually be written as the average of 4 points close by. And this means that indeed it's not a local minimum or maximum. It must be the average of its nearby points. Of course, we can actually generalize this argument to a stronger argument, saying that a point in the center, we can evaluate the scalar potential, and it equals to the average of a circle, where this circle encloses this point, and the point is the origin of that circle, and is the center of the circle, and the averaging potential along this circle is actually equal to the potential at the center. Now, this expression can actually be used numerically to calculate the Laplace equation. The idea is that first we set up a grid, and on the grid we can apply this formula, and starting from a random guess, saying that we can specify the v in the linear region to be a minimum or, and specify correctly the boundary values. Now we can iterate over this inner region and replace the initial guess of minimum by this average of the neighbors. And now if we apply this to all the points, and that means one iteration, and we iterate this over and over and over, eventually we reach a steady state where the distribution of Vxy does not change at all. Then at that moment we claim that the Laplace equation has found its solution. Now you can double check this at home using your favorite programming language, and here I actually try to solve this problem using Mathematica, and here I'm telling Mathematica to solve the numerical differential equation, and this is the Laplacian term applying on the uxy, and I let that to be 0, so we get the Laplace equation. Now I specify the u0 to be 0, and specify u1 to be 0, and I specify y equals 1 to be a sine function, and y equals -1 also to be a sine function. Now Mathematica can solve this and give a numerical solution, and on the right hand side is an analytical solution. You can compare the two and find that visually they are the same. You can also notice that the upper value and the lower value on the boundary are 1 and -1. So in the region that's excluding the boundary, because there are no maxima or minima, it's must in between this -1 and 1. We can see clearly that all the colors are within this color bar. And here I visualize the results in 3D. You can see that here on the edge they are 0, and on the other edge this is simply the sine function, and what's inside is simply the smooth average. This function actually, the Laplace function, can not only be seen in electrostatics, it can also be seen in many other places, such as the heat distribution or the heat equation. And say that in the classroom the heat distribution could reach a steady equilibrium, considering even though that there are air conditioning coming in and the human is dissipating heat. Suppose that we reach the equilibrium, then the guiding function for the temperature distribution should be the Laplace equation. And you can imagine that in between you and the air conditioner, the temperature must be sort of between the air conditioning temperature, which is quite low, and the human temperature, which is quite high. And the temperature can never jump above the human temperature or drop below the air conditioner. However, when you are calculating the Laplace equation numerically, you have to be careful that if you didn't have a dense enough grid, your results might be slightly off. So you can see that here I'm plotting the difference between the numerical solution and the exact solution. And the result difference can be up to 0.0005. However, I want to say that this difference is there simply because of the finite grid size, and if I reduce the grid spacing and say that here I enforce Mathematica to use a smaller grid, then the result is much more precise. You can see that the maximum error is about 2 times 10 to the minus 6 now. And that is because that our numerical methods, when we are calculating the Laplace equation, we have this OH to the power of 4, and this term is only approaching 0 if h is small enough. Now let's go to the 3D cases. Again, in the 3D, I claim that the Laplace equation allows no local maximum or minimum within the region of interest, and all the minimum or maximum should occur at the boundary. And to prove that, we can actually look at the average of VR over a sphere that's centered on R but at a radius of R. So that's similar to the 2D case, but except that we go from a circle to a sphere. And now we are looking at the average potential on top of this sphere, the shell of the sphere, and compare that with the potential at the center of the sphere. The claim is that the center potential should equal to the average of the potential on the sphere. To prove that, we can actually simplify the problem for a little bit. So instead of looking at a complicated problem where there are charge distributions on the outside of the region of interest, we simply say that because of the superposition principle, and if we can get this term right for a single charge outside this region of interest, then it can be valid for any charge distribution outside. And so the simplified problem can be solved using a technique that we used earlier in the lecture 3, I guess. So we can, without loss of generality, first we bring this charge of interest to the z-axis, and now we have this center located at the origin, and there is an r prime vector that's pointing at the scalar potential at the sphere that we are trying to integrate over, and this potential can be given by this separation vector, and this separation vector can be expressed using the same old expression, the law of cosine, where we simply express this separation vector curly r in terms of z over here and the r and an angle in between. Now, if we integrate this over the entire surface of the sphere, it can be written as the integral over 0 to pi and the integral over 0 to 2 pi d phi d theta. And here I actually missed r squared sine theta. And if you finish this integral, you can see that the final result should actually be a pretty simple expression. And you can see that this term is the theta evaluated at pi, and this term is the theta evaluated at 0, which is very similar to the expression that we solved in the lecture 3. And in the end, the result is only dependent on z. And if you stare at this enough, you can actually see that this is exactly the point charge potential at the R position, and that actually proves this the average expression for a point charge. And then using the superposition principle, we can generalize this to an arbitrary charge distribution outside. Then this arbitrary charge distribution can generate a very complicated potential on the surface. And however, if you average this out, this will give you precisely the potential at this center of the sphere. Now, this means that indeed, in 3D, still the Laplace equation doesn't have any minimum or maximum. So you may wonder, why do I repeat this no local minimum or maximum over and over again? Well, the reason is that actually we can use that to prove two uniqueness theorems. So the first unique theorem is that the solution to the Laplace equation in some volume can be uniquely determined if the V is specified on the boundary of the surface S. Here, this means that suppose we have a volume and the edge of this volume is the surface S. As long as the potential V on this S is determined, we can calculate the potential inside this region, and what's inside should be a unique solution, and there are no other solutions. So this is actually can be think of a generalization of the Laplace equation in 1D. So remember that in 1D we only need to specify the V, the scalar potential on both two ends at the boundary. Once that's specified, what's in between is the straight line that's connecting the two ends. Now, these two boundaries, single point becomes the surface in the three-dimensional integral, and the straight line becomes the volume. To prove that, we can actually use the proof of contradiction. So that is, suppose there are two solutions that both satisfy a Laplace equation. So del square V1 equals 0, del square V2 equals 0. And what we can try to see is what the V3, the difference of V1 V2 should be. Now, because the V1 and V2 both at the surface should be the same, which means that the difference of the V1 V2 at the surface should be 0, and that is the V3 at the surface should be 0. Now, because V3 is 0 at the surface, this means that the minimum of this V3 across all this volume should be 0, and the maximum of this V3 across all the volume should also be 0, which means that the V3 should be 0 everywhere. And this means V2 and V1 are really of no difference, and they are the same solution. This theorem can actually be extended, so in the sense that if there are some additional charges inside the volume, and then the Laplace equation is generalized to Poisson equation, and however, because inside we have the superposition principle, the vector, the scalar potential V at the edge determines the scalar potential in the volume inside without the volume charge density rho, and then that gives us the first piece, that is the V that depends on S, and then we get the another piece that's the contributed by the charge density, which is shown here. And now the total V should simply be the sum of the two contributions because of the superposition principle. And this V still is a unique solution. Now, this corollary can be applied to the problem, say that there is a point charge in the region of interest, but there is a conductor that is grounded, and now in this surface of interest, in this volume of interest, there is a single point charge, but the solution of this problem can still be uniquely determined because of this corollary. This problem is the can be solved by a method of image that I will discuss in the next lecture. Next, I want to discuss a second uniqueness theorem. So it's not every time that we can specify the voltage on the boundary. Sometimes on a conductor, we don't know exactly what's the voltage. Instead, we sometimes know what's the charge that we put on without knowing the charge distribution. And what we want to claim here is that here there is a volume that's surrounded by a conductor, and it contains some charge densities inside, and we can actually determine the electric field uniquely if all the total charges are given on each conductor. Now, to prove that, we need to check the electric field. Again, it's the proof by contradiction, and so suppose that there are two E field, E1 and E2, that satisfy this equation. Then because of the same Gauss law for E1 and E2, we can apply this Gauss law to all the surfaces that enclosing Q1. So if we integrate E1 across this right out edge of the conductor, we get the total charge equals Q1, and that is the same for any of this surface of the conductor. And if we calculate the difference of E1 and E2 over all these conductors, the difference is 0. And now we can define what's the difference of E1 and E2 as E3, and the E3 has a corresponding scalar potential V3. Now we can apply a trick that we can integrate over a volume of this quantity, and here the volume is the volume of blank space. So here I'm specifying the volume as all this blank region, excluding the shaded region. Now this volume integral can be transformed into a surface integral, and this surface must include the surface enclosing Q1, surface enclosing Q2, and also the surface enclosing the outermost region. Now let's look at what's the volume integral. So we can apply this del operator to V3, and we can also apply this del to the E3, and this del dot E3 should be 0, because there are no charge within the region of interest, and this del V3 gives negative E3. So the total volume integral results in this form. And on the right hand side, we can see that this V3 should be a constant over any surface integral. So here this surface includes the surface that enclosing Q1, surface enclosing Q2, and enclosing all of these conductors, and also there is the outermost surface. However, for all this volume, for all of this scalar potential, the V3 should be a constant and can be pulled out of the integral. And what's left over is the integral over E3 dot dA. Now we have the relation over here that E3 dot dA must be 0. So the integral is 0 on the right hand side, and this means that E3 squared must be 0 with the integration over the entire space V. And this is only possible if V3 is everywhere in this blank region, or we can claim that V is the region of interest. Now we prove that the E3 is 0 anywhere inside this blank region, so the corresponding V3 should be a constant inside this region. And then really the E1 and E2 should be of no difference, and the electric field itself should be a unique field. Now to summarize, today we evaluate the Laplace equation in 1D and 2D, and we try to numerically solve the problem in 2D. In solving the problem, we simply use the result we derived over here. And this, if we iterate this formula over and over and across all the space, eventually we get a steady solution, and that gives our numerical solution to the Laplace equation. We also derived two uniqueness theorems, and we hope to apply this uniqueness theorem to solve the problem of image charge over an infinite conductor. This is the problem that we want to solve in the next lecture. So this is not done yet.